community. Sylvio has finished the PhD in Université de Sorbonne in 1967, and is one of the milestones of our dynamic astronomy. So Sylvio is editor of many, referee editor of one of the most important journal in orbital dynamics, is the creator, of a big meeting in Brazil about this orbital dynamics that exoplanetary stuff is published over there too, and is astronomer that has a asteroid in his name. It's 16201. Yeah, by the way, has one of these asteroids that was put in homage to Professor Ferraz. So it's a pleasure. It's a pleasure to present you and go ahead with your talk. Thank you.
Well, good afternoon. I thank the organizers for the invitation to talk to this select audience. I am very glad doing it. So I will talk about the interactions between exoplanets. In fact, I will focus on exoplanets, not on solar system planets, with their host stars, and how they influence the star. Well, I will start just reminding what means tide. Tide is a universal phenomenon that happens every time that you have an extended body embedded in a gravitational field. So the body is being attracted by some strange thing from outside, doesn't matter what it is. So the part that is closer to this, the force is larger. In the other side, the force is smaller. So if I put my reference system in the center of the system, what I see is one small force in this direction and then one small force in this direction. The body is stretched by the gravitational field. This is tide in general, and it happens practically in every body in the in the universe in one way or another. If I have a spherical body that is attracted by a close-by body, so it will be deformed, and because of the differences of the closer and the farther points, it will take a kind of an oval shape. But in general, this it must be very, very close to have some asymmetry. Otherwise, what we have is a distribution that is more or less the same of the two sides. Okay, here, what happens here is more or less the same what happens in the other side. In general, we can, except for very, very special cases, we can neglect the difference between the two sides. This has been done, this has been used by astronomers since about 200 years. Everybody knows that the Roche limit, the Roche ellipsoid, the problem, the form that takes the body when deformed by a gravitational field. So I will, don't pay, okay, pay attention to the equations. They are not there for nothing, okay? But I will not make algebra or mathematics here. The equations are shown as illustrations. So if I have one external body acting on one extended body, what happens is it is deformed. It becomes a triaxial ellipsoid. Okay, the oblateness of this, the prolateness of this ellipsoid. So if I take the equator here, so is given by this equation. And this has been discovered by, has been calculated by Jeans about more than 1 century ago. In the static case, so if this body is stopped in this place, so this figure will be symmetrical. If it is symmetrical, no torques appear, nothing appears. You have a deformation, a constant deformation, and that is all. However, if this body is rotating, let us say, in counterclockwise, okay, if it's rotating like that, so it is rotating like that, what happens is that the deformation follows the rotation. The body is not a perfect fluid. If the body was a perfect fluid, it would ignore the rotation, it would continue to be symmetrical. But if it's not a perfect body, if there is some viscosity, the symmetry will be broken. And the symmetry is broken, then this gives origin to one torque, forces that are not a binary of forces. Main consequences. First, the loss of mechanical energy. The body is being stretched and then it changes the matter, let's go. The matter that is here, for instance, now is here, but alpha revolution later it will be there, that is closer. So the body is being making this, okay? So this generates heat in the interior of the body. And so the first consequence is the loss of mechanical energy. Mechanical energy is transformed into heat due to the tidal stretching of the bodies. The second important effect is the exchange of angular momentum between the relative orbital motion of the bodies and their rotations. So, this body will, in some way, break the rotation of this one. See, if this one is rotating in that direction, the torque will try to bring it back to the symmetry, okay? So, the rotation of the body will be broken. But Newton, action and reaction, if this body is provoking a torque in this one is also provoking a torque in this motion of this one. And so the orbitals also will be affected. So it will be an exchange of angular momentum between the rotation of the body and the orbital motion of the other body. Always in the sense that the faster give angular momentum to the slower. Examples in our solar system. Earth-Moon system. You look at the moon, you see St. George, okay? And the dragon, okay? It is there. If you look 15 days later, when the moon gave half a turn around its center, it is there. The shape, the figure that you see from Earth is always the same. Why? It is always the same because the motion of rotation of the moon about its axis and the orbital motion of the moon are synchronized. So the moon is rotating like that. It is rotating, but we see always the same side. Because of the reaction, so the Earth breaks the rotation of the moon, the orbit of the moon around the Earth is also being affected in the same sense, and the orbit changes. coming, sorry, I jumped about one of the lines there, one important line. Well, when I say the moon rotating about the Earth, I am thinking about the tide of the effects provoked by the tide on the motion of the moon. But the moon is also attracting the Earth. So the moon also is provoking tides on the Earth. And we know then because we have some a liquid layer above the Earth where this effect is increased. So what happens is that the Earth also is being, the rotation of the Earth is also being broken, but very slowly. So the duration of the day grows by 2.4 milliseconds every century. So it's almost nothing. Okay, this is almost nothing, but if we look at some evidences from geology, if you look at some formations on the Earth, we see we can compute we can have an indication of how was the rotation of the Earth some millions years ago, and when we count the layers of a coral reef, okay, we see that if this reef was formed 300 million years ago, then the day was 2 or 3 hours shorter than it is now. The day was 20 hours or 20 of our current hours. Reciprocally, we are affecting the motion of the moon around the Earth, and the orbit of the moon changes by some millimeters every year. So every year, the moon is being a little bit faster, and the eccentricity of the orbit of the moon is also modified. The other, these are effects of this exchange of angular momentum between the rotation of the two bodies and the orbital motion of one around the other. The other effect that I told, this the energy, the heat that is liberated in the affected body, you see, for example, when we study the satellites of Jupiter and Saturn, often you see the news, people had just discovered that there is a liquid ocean inside the body. There is a layer of the body that is liquid. You probably have seen the pictures of the geysers in Enceladus that are water that is being jets of water to the space, and this is exactly the heat that is being generated by the fact that the satellite is close to a very big planet, and it is being stretched by the planet in a variable way, and so heat is being mechanical energy of the orbital motion is transferred to the interior of the body, increases its temperature, and the ice of the inner layers becomes liquid, and this forms the oceans. So we have examples in the solar system of the tidal effects. Why did I consider these examples on the solar systems? I'm not interested today in speak about the solar system. The problem is that in the solar system is the only place where we have direct evidence of the action of the tides. So we have a phenomena that show this phenomena is the result of a tide. In the case of exoplanets, there are just, I think there are 2 or no more than 2, maybe 3 cases in which we can see that the planet is falling over the star. The planet is slowly falling off the star. So we compare the period of the planet around the star now It is being observed, so we can do it now. And if we compare with observations that have been done 10 years ago, what we see is that the period is decreasing. So the planet is slowly spiraling towards the star. There are one or two cases. In general, we only have indirect evidences. And about these indirect evidences is, in fact, what I will talk today. So, the first theory that was established to study tides was by George Darwin. George Darwin was the son, one of the sons of Charles Darwin, of the evolution theory. Darwin did something very close to what I will show here, but he was dismayed in some sense by the amount of calculations to be done. The paper, the Darwin's paper is 200 pages, more or less, of calculations, 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 and calculations, okay? Algebra, done by hand, okay? So it took a simplification of the problem, and the simplification of the problem is the following. Well, here is the body that is being deformed by the tides due to this body here. So since he is rotating faster than the orbit, I will have the deformation, the high tide, okay, the vertex of this ellipsoid will be displaced of an angle epsilon. And then with this, he computed the forces, the torques, etc., and could study what happens. Problem. The calculation of this angle epsilon is complicated. So it took an ad hoc tidal lag. Okay, let us assume that there is epsilon equal to, okay? Let us see what happens. The theory that I use well, all these theories, there are lots of theories to compute tides. They are more or less equivalent. They are not exactly equivalent, but mainly when we consider problems like I will consider today, giant planets and stars that are fluids that with some viscosity but follow hydrodynamic laws. So in these cases, I can get rid of the ad hoc lags and compute for every moment how much is the lag. So I can obtain the tidal evolution equations from physical laws. So with physical laws, I compute the angle epsilon, and then with physical laws, I compute the consequences of the deformation on the body. The base of the theory is very simple. Suppose that this line that is here is the actual surface of the body. So let's discuss this curve here, the actual surface of the body. This is the actual surface of the body. But this is not an equilibrium surface. The equilibrium surface is that one. If the body was a perfect fluid with no viscosity, it will have this shape, not this shape. So there is an ideal surface here that would be the surface of the body if it was a perfect fluid. That surface is this one. What says hydrodynamics? Hydrodynamics says that if I have a glass with some fluid and I turn the glass, the fluid will move to become horizontal again. But it can move very fast. For instance, for water, it moves very fast. But if I have honey in my glass, it will move very slowly, okay? But it will move towards the equilibrium situation. So this kind of flow was studied by Newton in the beginnings of mechanics, and is named Newtonian creep. Since I am in Brazil, it's important to say how we translate creep. In Portuguese, creep is fluência. It's not a word that we use many times in Portuguese, but the correct translation is fluência. Sometimes if you look a reference in Portuguese to this, look for fluência, not for creep. So this is the Newtonian creep. What he says? He says the following. This point, well, this is the actual surface of the body. The actual surface of the body tends to move towards the ideal one with a speed that is proportional to this distance. If it is very close, it will move more slowly. If it's more distant, it will move faster. This quantity gamma is just a coefficient of proportionality. In this case, is a relaxation factor. Okay, if we take this that I have told and consider a simple problem, consider a simple scheme, and we'll look and apply the equations of hydrodynamics in this case, well, first, we have to happily, we are in the motion is very slow, so we can use a low Reynolds number hydrodynamics. So I don't need to use the Navier-Stokes equation. We use an approximation of the Navier-Stokes equation that's named as Stokes equation. That's not the inertia. It's not able to produce turbulence like in other fluids. So we can apply this. Take the solution of the Navier-Stokes for this solution, and we get that the relaxation coefficient is proportional to the mass of the body, to the gravitation on the surface, and inversely proportional to the viscosity of the fluid. So if I have a more fluid or less fluid body, I will have different values of gamma. So in the more simple case, so I will take this. If you look at this, look, this is a differential equation. I have the variable zeta, and I have the derivative of it here. So I will develop this. Rho that appears here is the surface in the static case, in the case that it would not follow the direction of the field, the rotation. It would not be influenced by the rotation. So I know the equation of the ellipsoid. I will put the equation of the ellipsoid. I know how it moves. I will put the equation of the motion there, and I will have to start this equation here. This equation here seems complicated, but if you remember, it's no more complicated than the equations that you learn in Calculus 1 or Calculus 2, or Calculus 2 or 3, you know? One is too early. So it is linear. It is linear, so the derivative plus a constant times the variable. This side, and this side is a function of the time. This function is, okay, the parameters of the bodies. R is the distance between the two bodies. So this is given by I say this is a Keplerian motion, for instance, so I know how this distance will change. And V is the angle, opposition angle of the body in its orbit. The other angle that appears here is the angle that fixes the position of the ellipse relatively to the body. So the rotation of the body will enter here. So what is this? This is a known function that depends of the time. So, sorry. This is a linear differential equation with constant coefficients. Gamma is a constant, with right-hand side, non-homogeneous. Okay? Non-homogeneous, because there is a right-hand side that depends on time. Well, this simple equation, when we develop it, it becomes monstrous. Okay? Even the code to compute the results are several pages of coding to get numerical results of it. So what's the recipe? Recipe is, so we integrated the differential equation. So this is a linear equation. We know how to integrate this. Okay? Every book on calculus give this result. Okay? For those that are very good students in calculus, you remember of integrating factor. The integrating factor is this function that appears here. So it multiplies the right-hand side, and we have to integrate it. After integrating it, let's some examples. I will see that. I will take an example here of a slow rotating sun-like star, period 30 days, Ostiga hot Jupiter. This planet is in a 4-day eccentric orbit, A equal to 0.2. So the orbit is elliptical. So if I integrate this, I get this kind of figure. For instance, this is the relative value of the prolateness of the equator of the planet. So you see that this prolateness has a big variation. So the planet is making like that. Okay? If I take a direction in this direction, if I take the shape of the ellipsoid, it's changing sometimes because I consider it an elliptic orbit. So if I consider an elliptic orbit, sometimes the planet is closer, other times it is farther. The distance is oscillating periodically from the maximum to a minimum. So the body is making like this. Okay, it's stretched, less stretched, more stretched, less stretched, and so on. So, on the other hand, if I look at the position of the axis of the body, okay, so I see that this angle is also changing. So the angle delta is not constant, but it has a small variation. So I can then now I know the shape of the body. I can compute which is the force which the body acts on the other one. Okay, compute the force and the torques due to the tidal deformation of the bodies using the solution of the differential equation that I get there. Next, I integrate the variational equations of the orbital elements. These are equations that comes from celestial mechanics, from the motion of the body. So I can know how the orbit of the body will change on time. Okay, I put just a simple 1, 2, 3, the 3 steps, but some of them are a lot of computation to do. Oh, example. This is the equation for the momentum. I get this equation here. When I make these substitutions, I see that the variation of the rotation of the body is given by a series of this kind. As I told, don't worry yourselves with the contents of every equation. This is just an illustration. What happens is that if I take this and I look this at the neighborhood of when I make the question, when omega dot equal to 0, when the speed of rotation will be equal to 0. It will not vary, excuse me, okay? So I will get a kind of the kind of figures of this kind. Well, this is the equilibrium. This is the point where omega dot equal to 0. These are the values of omega. In fact, not of omega, but omega minus constant. Let us say, the distances of omega from 0, okay? And in the vertical, I have omega dot. So what happens? If I am on the left side of the figure, lambda dot is positive. So if the rotation of the body is in this side, the velocity is positive, so it will vary in this to the right. Okay? The velocity is positive, it goes to the right. If it is on the other side, it's the contrary. The velocity is negative, so it is on the positive side of this axis, so the velocity is negative, it will move to the left. So from the side it moves to the left, from the right it moves to the left, on the left it moves to the right. So in the middle I have this point is a point of stable equilibrium. Okay? If I take the motion from this position, it will be back from this position quickly. But one important detail. This is the case when the eccentricity is equal to 0. This equilibrium is exactly what I have shown in the example of the Earth and the Moon. I have the two motions, orbital and rotational, that are synchronized. So the two are synchronous. This is the situation of the equilibrium that shows the Moon. But if I take a motion that is on a eccentric ellipse, what happens is that this point moves here. You see, it's more here. I don't see exactly. Here we see that it's a little bit more to the right. But when I put here the eccentricity 0.5, the equilibrium point is here. What does it mean? Does it mean that in real cases, there is no exactly synchronization of the rotation, because it will not become synchronous with the orbital motion. The equilibrium point is on the right of the 0, so it is faster. It is faster than the synchronous. It is super synchronous. It is moving a little bit faster than the orbital motion. This is the situation of equilibrium when I have an eccentricity that is different of 0. Well, examples. First example. I have chosen the examples here with very heavy bodies. I don't consider, well, first, very close planets to the stars, like we are discovering every day currently. And the companion is a heavy companion. So in these two examples that is here, the companion is not exactly a planet, but a brown dwarf. It's more heavy. the first case, Corot 15b, the mass is 60 times the mass of Jupiter. In the second case, Kelty 1b, the mass is 27 times the mass of Jupiter. This is because the storks that I have shown you some illustrations, it is proportional to the 60th power of the distance, to the inverse of the 60th power of the distance. So if it is very small, it's enough that the distance is a little bit larger and you have the result zero, practically. You don't have any more effect. So to see the effect, I have to look for masses that are big. If I put here a planet like the Earth that is 1,000 times smaller than one of these ones that I am considering, or 10,000 smaller, so I will see nothing, okay? So the effects are not, we cannot observe the effects. To observe the effects, I need the objects very massive. So in this case, the orbital period is 3. The star rotation is between 2.9 and 3.1. So we have almost coincidence between the orbital period and the star rotation. This is exactly what I have told for you in the case of the moon. For this one, the values are not exactly equal, but we have to pay attention to the fact that it's very difficult to get the information on the planets. And in this case, we don't know exactly the mass of the planet, okay? We know that the mass is equal to this number, 1348, but I have to multiply by the sign of the inclination of the orbit. Because if the orbit is inclined, I am not able to measure the real speed of the orbit, but just the projection of this speed on the line of sight. So, okay, but if you put here 0.9 or 0.8, we will see that this is one case that must be in which we apparently have synchronization. What happens with a body? Let's consider another example. This other example is the star Corot 3. Corot 3 22 times the mass of Jupiter. Is a brown dwarf. So I can take the theory that I have constructed and start playing in the computer to see what can have happened to this system in the past. For instance, if I consider, okay, I don't know which is the relaxation factor of I don't know the viscosity of the planet, or the star, sorry. I don't know the viscosity of the star. So I have to guess. There are some indirect evidences of some values. I have to guess one value for the relaxation, and they are given here. Well, no matter which is the relaxation, okay, in a large range, the star rotation it will be transfer of angular momentum from the orbit of the planet around the star to the star. So if I start here with the star rotating with a very fast, so rotating with a period of 2 days, so the star is rotating very fast, what happens is that angular momentum is being transferred from the planet to the star, and it will be rotating slower and slower, okay? And after some time, the scale of time is here, 2 gigayears, 4 gigayears, in a time that I don't know exactly because I don't know exactly which number I should consider, I see that they converge to this value. This is exactly the observed value, okay? So the star evolves in this way, so the star in this way. In the same time, there is the converse effect, in which if the orbit is if the tides are transferring angular momentum from the orbit to the rotation, the orbit is losing angular momentum. So the orbit will change also. So I see the period of the orbit, it also is increasing. The period is increasing. So the orbit is becoming slower and slower. And in the two cases, these are values that have been observed in the Corot mission. What is important here is, I didn't call your attention yet, is the following. This is a F7 star. This is a F5 star. This is a F3 star. These stars are very quiet. So I could reproduce what happens with these stars applying my model. But I will apply it to another star. I will apply it to Corot 33b. If I apply the theory to Corot 33b, which is also the planet, in fact, a brown dwarf with 60 times the mass of Jupiter, what will happen? The star rotation is evolving in this direction. The orbital period will evolve in this direction. But what I observe this. I am not able to reproduce the evolution of the rotation of the body and of the period of the body and get a result that is coherent with the values that are observed. Why? Something is wrong. And what's wrong is the following. What's wrong is the following. The star is not quite, the star in this case is a G3, no longer a F, like in the other cases. And G stars are not quite at all, like our sun. Okay, they are spitting matter to the space all the time. So this matter that is at a given moment on the surface of the star, rotating with the star, is thrown away. So it carries a little bit of angular momentum with it. So the star is losing angular momentum. So the fact that the star is losing angular momentum was not taken account in the previous calculations. So I have now to consider this. Well, this is the model given by the astrophysicists. This is the model given by Bouvier for the stars between 0.5 and 1.1 the mass of the sun. Recently, we have a similar study by Engel and Guinan for M stars. So, because this is important, because most of the stars are M and not G. So it's much more frequent to have a planet around the M star than a G star, because M stars are much more frequent. So if I want to study, then I cannot use this. I have to use the study of Engel and Guinan. In these studies, they follow exactly what has been told by Sidney today, which they draw C to determine the age of a cluster, of one cluster, using the rules of stellar evolution, and use this age to see how we can relate the period of rotation of the stars in the sample. And making this for several different clusters, they can have an idea of what happened with a star when, how much the rotation of the star will be breaked because of this angular momentum that it is losing. So now, if I include this in the model, so instead of just taking the exchange of the angular momentum between the star and the planet, I also say, well, but I have also, the star is losing to the space angular momentum. Then, in that case, I came back to the case of Corot, and you see now, I get the orbital period exactly the observed, and I can get the rotation, the rotation period of the star exactly as. So what happens is interesting that you see the star initially is rotating very fast. The period is small. The rotation is increasing. The period of rotation is increasing. So the star is being despinned. Think of the sun. The sun was not born with 28 days of rotation period. It was born with 2 days of rotation period. Because of the solar wind, okay, this rotation has, in 5 billion years, has become slower and slower, and today we have a period of 28 days. So exactly what we see here, not exactly the same numbers, but the period is increasing. But at a given moment, okay, it decreases, it starts decreasing slowly, and what the angular momentum that the star lost to the space is compensated by the angular momentum that it takes from the companion in orbit around it. So you start going a little bit faster. Here. So after 1 gigayear, the tidal interaction is stronger than the magnetic braking, and the stellar rotation accelerates. An old star. So very interesting, this figure, for the following. We don't know which was the speed of the star when it was created. Doesn't matter. No matter which value I take for the initial value of the rotation of the star, if the star is old enough, they will all converge to the same value. And coincidence or not, this is exactly the value that we observe, that is observed, in this case, from ground. This is a planet observed from ground. Another similar case, the rotation grows to the value of the observed here, and the orbit is here. And so the rotation, so the rotation goes to an equilibrium which is much slower than the motion of the orbit. No? Again, this is a G star. Well, let us try to see other consequences of the tidal effects on exoplanets. This is a picture that has been published 10 years ago by Macmillan, etc. One good thing for us from the observations of planets done by space probes, by spaceships, okay, by telescopes in space. In this case, I have shown several examples of stars that were discovered by the telescope Corot in space. Now I will talk about stars that have been observed by the telescope Kepler in space. Corot was a toy telescope of 20 centimeters. Kepler is American telescope, 1 meter of diameter, and able to see very, very, very faint stars. But the problem is that the stars are very faint. And in many cases, we are not able to we could even observe them from Earth, but we cannot get telescope time to observe 5,000 stars from ground 300 days per year. So we are not able to determine the characteristics of each star. So so let's see what we can get from the the observations done by the Kepler. Well, we can get the periods. We see this telescope is measuring the light that comes from a star continuously. So it measures the bright of the star during a very long time. If the star has eclipses, if it transits, if a planet passes in front of the star, so it is looking at some value of the brightness, and the brightness has a dip, becomes smaller, and then come back to the normal value. So something passed in front of the star. So if this repeats several times, we can measure the orbit, the orbital period of the star. Okay, so without the need of ground observations, we can have the orbital period of the star. Also, if the stars are active, like it was shown, some kind of activity, like it was shown in one of the previous figures, so look at the sun. The sun has spots, okay? The spots are moving around the star. So when the star is rotating, sometimes it shows more spots to the Earth, sometimes it shows less spots to the Earth. So the intrinsic brightness of the star has a small variation. Okay? So I studied this small variation of the brightness of the star, nothing to see with the planet, but this variation allows me to know the rotation period of the star. So this has been done for a large sample. So this has been done for a large sample of the planets that have been observed by Kepler. And this figure has been constructed. It's important in this figure is that the color indicates the temperature of the star. So it indicates the type of the star. It was interesting to see, first thing is that the blue, there are several systems which appear in the lower part of the graph. The lower part of the graph is rotation period between 1 and 4 or 5 days. So very, very fast rotation. So they are all blue. They are all very hot stars. So they are probably all of them F stars. So they don't have the activity that has been shown before. On the other hand, for the other stars, with other colors, there is colder stars here. They are active, so they are spitting matter into space. They are losing angular momentum. So the rotation, the period of the rotation is growing. So it's losing angular momentum, so it's losing angular velocity, so the period is increasing. So the normal evolution of one of these stars is from a period initial that we don't know to periods that are 10, 20, 30, 40, 50 days. So very long periods compared with the initial periods. This is this picture. Let us see if we can get something more from this picture. If you pay attention, you see there is agglomeration of big dots here. Big dots are stars with radius larger than 10 times the radius of the Earth. Okay, there is an accumulation of them here. Okay, you say there are big dots all over the figure, but they are scattered, while here they are grouped. Okay, there is a group of planets, of planetary systems with giant companions, hot Jupiters around them, with these periods large and with these orbital periods here. Okay, let's continue. Well, first, this figure has been updated by Christian Bourget using a more rich sample of data from Santos et al. 2021. And so this is the same figure as before. just done with more data. And we see the accumulation in this region. Well, I will now take our program, our codes. I will consider that I will consider a sun-like star, so it is losing angular momentum. So the period is increasing. And I will follow several of them, starting from an arbitrary initial condition. What I see, if one system starts here, let's say the orbital, the orbital period, let's start here. The orbital period is 3 days. So it starts with 3 days around the planet is 3 days around the star. What happens is that, okay, the star is losing angular momentum. The star is being bracketed by the wind, so it grows. The period of the system increases. The effects are more or less not apparent in the orbit. But at some point here, in this case, this corresponded to a star with an age of 6 gigayears. The star stops. The period of the star stops growing. It starts decreasing, and the planet starts falling on the star. Okay, and if you see these curves, you see that the turning point in every case are all in this region. Are all in this region. So we have some justification for the existence of this clustering of giant planets in this region. Look, okay, but it would be enough to speak of the breaking to justify. No, the breaking would justify that they are growing. But why in this side they grow higher, and in this side they stop a little bit earlier? Okay, here they grow, they continue. I can go 10 gigayears and the star is there. But because of the tides for these stars close to these planets close to the star, after some time the planet will fall on the star. So we have some kind of confirmation of that the existence of this accumulation is due to the tides, to the transfer of angular momentum from the star to the planet and vice versa. Okay, this is for hot Jupiters. Let's take smaller planets, like Neptunes, small Neptunes. So planets with masses that go between, what's given here is the radius. Planets whose radius is 3 times the radius of the Earth. In the case of the hot Jupiter, the radius was 11 times the radius of the Earth. Now I will take smaller ones. If I take smaller ones, I have the same phenomenon. And look, now, okay, these ones are more or less not affected, the small ones, so they will just grow because of they will just go up in this plot because the vertical axis is the rotation period of the star, and the star is losing angular momentum independently of the body that is aside of it. But if I take the ones that are close to the stars, I see the same kind of thing. But now, they quickly fall. So we don't have a kind of agglomeration. No? They are more or less scattered in this region. This is scattering just means, okay, every one of these stars are in transit towards to fall in the planet, to order the situation in which they fall in the planet. This one's more slowly, this one's more quickly. So this region is void. The similar region here is not void. There are not many bodies because of the increase of the period, but here, no, this region is completely void. It is so, again, we have a similar situation. Okay, taking a little bit smaller ones, 1.6 Earth radius, I have the same thing. I finished it, but I have one more point to show because it's very interesting, taking into account what is being told with the teacher by Sydney in this course, in this meeting. So I spend a lot of attention in this region, explaining why I have this here. But what is this? This is completely out of the plot. Okay, that is just one way of answering this question, is trying to see what this object is. This object is a subgiant. So while the others are the main sequence stars, this one is a subgiant. So what happened? It passed, he already entered in the region in which the star is expanding its sizing. It's no longer a normal star, it's becoming it's in the way to be a giant star. So it increases. So what happens with the dancer when it increases it stops. So since when the star is inflated to conserve the angular momentum, what happens is the inertia, momentum of inertia will increase, so the angular velocity has to decrease. The angular velocity has to decrease. It means that the period will be larger. So this star escapes from the rules that govern the other ones. Just as a curiosity, this was not the essence of the presentation. Thank you.
Excellent. Thank you, Sylvio. So we have time for questions, comments.
I have just one more remark. I am a little bit deaf, so please speak aloud and slowly.
Students want to have questions first, that's fine. But okay, right. That's quite interesting work. Thank you. I was wondering if you can go back to the slide 32, where you showed the evolutionary tracks of the Neptune mass planets.
Repeat, please.
On the slide 32, like 2 slides before this one.
32.
Yeah, you were showing the tracks of the Neptune-sized planets. I mean, this is fantastic. I mean, as we were chatting after lunch, right before your talk, there is a work that is showing that there is an overabundance of hot Neptunes at younger ages. Ages from like 0 to 800 million years.
Overabundance of Neptunes where?
For young stars compared to older stars. If you compare young stars to the stars in the field,
young stars.
Yeah, the young stars have more
would
hot
be here.
Neptunes than the older stars, and that's been kind of hard to explain. But it seems that this plot explains that.
I don't know if this is apparent in this plot.
No, but
because
it is.
the young stars, we should find them about here. So look. So this is the time scale given by the Cosmological law, by gyrochronology. So we are about here. this is the line that about 1 giga-year and more than 1 giga-year.
Right.
So if we go there, so this would be, so, well, I have not made any statistics of these dots, but apparently I don't see exactly.
Right, but from the slide that I was showing before, the one with the Neptune planets, the 32, were those red dots an evolutionary track on the slide 32?
No,
Two slides after
not see.
this one.
At least in the sample that has been used to do this work by these people, they are not seen.
32.
Slide 22.
32.
32?
Yeah.
So, I mean, 32 the slide.
No, but the slide is always the same. So,
This one there, yes, yes, right.
this is part of the other. This is just the part of the other. So.
Right, but that slide seems to show that as you go to older ages, then you lose the planets. Is it, so I guess the question is, what is happening at older ages? So the planets are getting close to the star because of the tides, and are they lost to the star?
Well, maybe the answer to your question is the following. Tidal effects are limited to this, to very close planets. Right. Okay? So if I take the full sample, so I don't know, the tides apparently doesn't affect nothing here. There is a small suspicion of some small motions in the blue stars, in the F stars, but not enough to be seen.
Other questions here, I guess?
So when you mentioned before that there are some planets in that upper region where the stars is becoming a giant, so it's a subgiant. You say that it's because it's slowed down because of the expansion of the envelope, right?
No, but not yet here.
Yeah.
Not
okay.
yet here. In this moment, if you take the models of the stellar evolution, Claret was the model used all the time for doing it. You see that in this period we don't have any important change in the star, in the size of the star.
Okay. I think I was when you mentioned that there are some planets found, some Neptunes found that have very low rotational, very high periods, rotation periods, and they are where it's.
No.
Where
Repeat.
I think one of the curiosity you showed at the last slides. Yeah, subgiants.
One.
Yeah, one. Yeah.
Yeah.
Now I was thinking like, but when the star expands, also tides become more efficient.
Yeah.
So we should be lucky to find.
But you know what we are seeing is what happened in the past. Okay. Now I will just be thinking high voice. Okay. So he is growing here normally, but then it becomes it reaches it starts to become a giant, and then it changes places. So no tide is involved. Just evolution. Just evolution.
Another question? So, yeah, I have one. Sylvia, about the gamma. I mean, gamma is quite important, right, for the tidal. So,
yes.
Can you say something about the gamma that you found from this?
No.
It's just
No. What happens is that making plots like this one, for instance, if I look at this is a kind of is more or less the way in which the gamma are determined. We see which the gamma is necessary to have things happening, okay? And this has been done not only with this phenomenon, but with several others. And always we get results that correspond to a values for G star, sun-like star, values of gamma that are around 10 seconds to minus 1. Between 10 and 100 seconds to minus 1.
Sounds good.
But this is determined to be such that things happen. We don't have a way of determining gamma from other data.
So good. Anything else? So thank you, Sylvia, again. So what the next? Ricardo,